Hello everyone, and welcome to the channel. This video is going to be part 1 of building the clock for the CPU. I hope you enjoy. Okay, so in the past few videos we've been working on this demultiplexing circuit, and now that it's done I want to move on to something else, and that's going to be the clock. So we've already discussed the use of this clock frequency divider that we need in order to get a synchronized clock and inverted clock for our demultiplexing circuit. And that means that we need to input twice the frequency that we want. So what I want to do in this video is start thinking about the clock and how we're going to build it. So first what I want to do is go over some goals. My goal for the clock circuit is to build a pretty full-featured clock. So I want to be able to reuse it for different projects, whether it's 6502 or 65816 builds, or custom CPUs or anything like that. So I'm going to need 3 different clocks. One fast clock, which is going to go from around 1 megahertz to 14 megahertz, which is the maximum that the 65816 can take. One slow clock, which is going to be for blinking lights. You're going to be able to see what's happening in the build. And one pulse clock, which is going to be just for single stepping with a button. There's going to be 2 selection buttons. One for the modes, whether it's free running clock or pulse clock, and one for the speed, fast or slow. I want to make sure that we have clean clock switching. So that means no switching in the middle of a cycle so that we don't break any running programs. There's going to be a hold line, which will stop the clock until reset, and a break line, which will switch to pulse mode. The goal for the break line is to be able to programmatically activate it so that we can put breakpoints in the code. And then I want the power-up behavior to be configurable via a dip switch. Which mode and which speed should it take on power-up? It depends on the situation, so it would be nice to be able to configure this. And as I mentioned earlier, the output stage is going to be a flip-flop, so that we have a 50-50 duty cycle. That's really important. And then we can get a synchronized inverted clock. So that's going to be a pretty full-featured clock. Let's start building it. So I'm going to start building things in KiCad first, and then when it makes sense, I'll do some tests on breadboards. But this way we're going to be able to move a bit faster. So first thing I want to do is create a hierarchical sheet to contain the clock. And I'm going to take this circuit and copy it and move back this gates to the unused gates and delete all of this. Okay, let's get started with the clock. So this is going to be our output stage. I'm going to set up the outputs. And now if I move up, I should be able to import the pins. There we go. And so I should be able to re-add my labels here. There we go. Okay, so let's take a look at the datasheet for the 65816. And see if there's anything we should keep in mind with the clock circuit. So there's nothing special in the phase-to-in clock inputs that we should keep in mind. It just says that the clock can be held in either state to preserve the contents of the internal registers. So that means that it's a static design. Let's look into the timing characteristics. For the 5-volt version, the maximum clock that we can get is 14 megahertz. Actually, that's defined as a minimum cycle time of 70 nanoseconds. And if you do 1/70 times 1,000, get a frequency of 14.28 megahertz maximum. So it's a little bit over 14 megahertz. That's going to be useful later. The other specification that we have is that the fall time and the rise time of the clock needs to be at maximum of 5 nanoseconds. So that requires a pretty fast chip. And so it's pretty difficult to actually find data on the fall time and rise time of 74 series chips. But I was able to find this AHCT Designer's Guide from 1988. that shows a graph of the switching performance of the HC gate that also includes HC and AC. And so we can see here the different behaviors of the families. So the AC gate is the fastest, but it also has a pretty big bounce, and it's also pretty noisy. There's another graph just below that shows the ground bounce of those different families. And so the AC gate is the noisier. So I want to try to avoid using AC gates when I can. So you can see here that the HC gate has comparable speeds, but it's a much nicer slope, comparable to the one of the HC gate, which is much slower, but it also has a gentle slope. So will this work with the 5 nanoseconds rise and fall time requirements of the CPU? So I put this data into a spreadsheet in order to compare it. The rise and fall time are defined as the time it takes for the signal to go from 10% to 90% of 5 volts. So that's from 0.5 to 4.5 volts. And so we can compute that using the slew rates that the graph give us. And so we can see that the HC gate is below 5 nanoseconds in both directions, but the AHC gate is a bit higher than what we want. And the AC gate is really fast. It only takes 2 to 3 nanoseconds to transition. So both the HC and the AC gate will work for this purpose. So now this raises the question of which of the HC gate or the AC gate is the best for our use case. Can we use the HC gate? Well, remember that I said that we have to input twice the frequency that we want at the output. So if we want 14 megahertz at the output, the input frequency needs to be 28. And if we look at the data sheets of the 74HC74 in the switching characteristics, you see that it has a minimum frequency of 25 megahertz over temperature, and it's actually 31 at room temperature. So using an HC gate to drive the clock would work, but it is pushing it a bit. So I'm going to use an HC clock because I know that the AC gate can have a really unclean signal, especially on a breadboard, and I want my clock to be as clean as possible. So I'm going to change this to an HC gate. Okay, so let's start working on the fast clock. So I'm going to add the crystal. And so the frequency of this needs to be 28 megahertz. Unfortunately, I wasn't able to find a 20 megahertz crystal precisely. I did find this 28.322 megahertz crystal, but I think this is fine because the datasheet of the CPU specifies a maximum cycle time of 70 nanoseconds. So 1 over 70 times 1000 is 14.285 megahertz. And remember that we are dividing our frequency by 2. So if I multiply it by 2, the maximum frequency of my oscillator is 28.571, which is above this frequency. So this should be fine for when we want to run at the maximum speed. So that's what I'm going to use. Pin 1 is a no connect. Then we need VCC and ground. I actually don't have ground yet here. And that's going to be our fast clock. So of course we don't want to run at this speed now. Remember, my goal for this project is to be able to run at 4 megahertz. So I want to be able to divide this clock down. So I'll go back later and do the frequency divider. But for now, let's focus on the other clocks and think about the slow clock. So for this, I'm going to use a classic 555 circuit. And I'm not going into too much detail on this circuit because it's been done already by a few people on YouTube. So for example, if you want to learn more about how this circuit works, you can go watch Beniter's videos. So we're going to pull the reset high. We're going to join the threshold and the trigger. Then we're going to pull up the discharge pin. And the values for this is TBD. I'll figure out the resistor and capacitor values on the breadboard. We're going to need another resistance here. I'm going to a potentiometer. And And again, the value for this is going to be determined. And so this goes back to the discharge pin, and then the other pin of the potentiometer we don't connect. And then the output is going to be on the Q pin. We need a little 10 nanofarad capacitor here. Going to ground, and another capacitor here. This is TBD as well. Okay, so this is going to be our 555 clock. We're going to be able to change the frequency of the clock using the potentiometer here, and it's going to be pretty slow depending on the values that we choose. This is a slow clock. And then the remaining clock that we have is pretty simple in theory. It's just a button with a pull-up resistor. No, actually with a pull-down resistor. And so this is going to be our pulse clock. When we don't push the button, this is pulled to ground, and when we push the button, it goes high. Now we have to talk a bit about debouncing. And so I'm not going to go into too much details on what debouncing is, because you can find good content already on YouTube going into detail on debouncing. So I will recommend this video from Robert Baruch called Chip Tips #1 Debouncing, where he explains in detail what switch bounce is and how it looks like on the oscilloscope. He also proposes a solution using an RC network going into a Schmidt trigger and does some math in order to figure out which component values to use. And he also tests it on a breadboard using a counter to make sure that the method is working properly. So I would really recommend giving this a watch. I'll try to remember to put a link in the video description. If you'd rather read some long-form content, there's this amazing series by Max Maxfield on EE Journal. It's a 9-part series on switch debounce, and it goes into a lot of detail, and I really recommend you to take a look at this. Specifically, the solution that I'm going to use, which is the RC network with the Schmidt trigger inverter, is detailed in part 3 and part 4, and you can see it here. So basically the way this works is that as you open and close the switch, you're going to have some bounce on the opening and on the closing, as well as potentially some noise when you're not touching the switch. Connecting the switch to an RC network allows to dampen this noise. You can see here when the switch is closed, the RC network is discharging. And then when you open the switch again, it charges progressively. And so this dampens the bounce noise. By using a Schmidt trigger inverter, you are able to clean up the signal and make sure that you only have one single edge on each side. So yeah, I really recommend reading this article if you want to learn more about how this works and why some other techniques, such as, for example, using a 555 timer for debouncing, doesn't really work properly. So Bad Eater, for example, uses a 555 timer in a monostable configuration to do switch debouncing. And so this kind of works, but it also can lead to problem because it doesn't properly debounce the switch closing. So when you release the button, if you have a bounce there and you have kept the button pressed longer than the duration of the pulse of the 555, then you can have a bounce there. So all in all, I think the RC plus Schmidt trigger inverter method is much more reliable. And so this is the one I'm going to implement. So we're going to need a Schmidt trigger, a capacitor, and then 2 resistors. The output of the Schmidt trigger is going to be our debounced clock. And then we still are pulling down the switch. There you go. So again, we're going to determine all the resistor and capacitor values on the breadboard. But this is our pulse clock debounced and ready to use. Okay, so now what we need to do is to build these circuits on breadboards so we can experiment and find out which resistors and capacitor values we need. and check that everything works. So this is what I'm going to do now. I'm going to start with a brand new breadboard. Let me bring in my power supply. This is going to be our oscillator. So it needs power and ground. Let's go ahead and turn on the oscilloscope so we can measure the frequency. So the yellow probe is going to be the output. I just noticed that my ground wire is at the wrong spot. Let's plug this in over here. So of course I need to connect the power rails. So I'm actually going to move this a bit. So the signal is not pretty, that's normal. It's my measuring setup is not great here with this long cable, and the breadboard is a bit much for 28 megahertz. But we do measure 28 megahertz, so that's pretty nice. I'm going to leave some space here next to the oscillator to do the clock divider later. And I'm going to start working on the 555 clock. So this is going to be our 555 chip. So I'm going to leave a bit of space here to do the frequency division later. And I'm going to put it here. Now it needs power and ground. Power is pin 8 and ground is pin 1. Then I'm going to tie the reset high, and that's pin number 4. We need a 10 nanofarad capacitor on pin number 5, going to ground. We also need a decoupling capacitor for the power. And I might as well add one for the oscillator here. Then we need to wire up pin 6 and pin 2 together. I have a little jumper here. Then we need a capacitor going to ground on the threshold. I'm going to start with a 1 microfarad capacitor. So that's pin number 2. We need a pull-up on the discharge pin, pin number 7. I'm going to do it with the 1K resistor. And so now the only thing missing is the resistor between the discharge pin and the threshold. And I'm going to try using this potentiometer I have here. This one is 500K ohms. Let's see if it works. Just going to wire it with jumpers now. So between pin number 2 and pin number 7. And we should be able to see the clock working on the output on pin number 3. So let me change the scale of the oscilloscope here. So we do have an oscillation, but it's not working properly. Oh, yeah, I didn't connect ground. Yeah, that's much better. Okay, so at a minimum, let's see what frequency we have. Also just going to add a LED to the output so that we can see what's happening. Okay. So this seems to be a pretty good low frequency for the clock so that we can see what happens on the board. Remember that we're going to also divide it by 2, so it's going to be twice as slow. And then if I go up, then we go to we go higher than 1 kilohertz, which is a bit much. So I'm going to add a series resistor with a potentiometer, because when this goes to 0, then the frequencies goes to a very high value. So what if I take pin number 2 here, And I'm going to add a small series resistor. So this is 220 ohms, and it should limit the maximum value of the clock. And yeah, that's pretty good. That it goes to around 1 kilohertz. Yeah, that seems to be a pretty good maximum value. So one thing you will notice is that the duty cycle of the 555 timer is really not symmetrical. So that's also why I want to add the flip-flop as an output stage in order to correct this. My potentiometer has not a great contact here. But as you increase the frequency, the duty cycle gets worse and worse. So I'm going to change the potentiometer because this one really doesn't sit well on a breadboard. I have here a 500K potentiometer that I'm going to try to use now. Let's see if it works. And this one is also pretty nice because it has tabs on the side, so that it's going to be pretty stable on the breadboard, which is one of the things that weren't really working well with this one. If I do this, so this is really good. So I'm going to wire this permanently. There we go. And now we have our 555 clock with a really nice potentiometer. And I'm actually going to switch everything a bit to the left. I think I left a bit too much space here. I don't need that much space for the clock divider. It's only going to be a dip switch and a counter. So yeah, let's move everything to the left. There we go. And it's still working. Okay, so finally let's work on the pulse clock. So I have here our 74HCT14 Schmidt trigger inverter. With it we're going to be able to debounce 6 buttons. So it's pretty nice. So it needs power and ground and a decoupling capacitor. And I'm only going to use one input for now, so I'm going to tie all the other inputs high. So we're going to need a button. That's going to go on one side to ground. On the other side, we're going to need a capacitor and 2 resistors. And so I have here a 4.7 microfarads capacitor going to ground. Let's think about this. And then the switch being pulled up to VCC with a 1K resistor. And then the junction of the resistor and the capacitor here is going to the input of our Schmidt trigger inverter. And then we're going to look at what happens at the output. So I'm going to connect the yellow channel to the switch, and I'm going to add my blue probe to the output of the inverter. So normally this is going to be 5 volts, and then when I press the button, it's going to go down. Let me change my scale a little bit. There you go. Add the third one. Okay, so the inverter doesn't trigger. Why is that? Because I'm in the wrong pins. So let me do a single capture. There you go. So as you can see, between the moment when I press the button and the yellow line goes low, there's a delay before the inverter goes high. And when I release the button, there's also a delay before the inverter goes high. So let's measure this. We have a 30 millisecond delay on the button press. and a 22 millisecond delay on the button release. And so, yeah, so this should work pretty well. In the ultimate guide to switch debounce, they mentioned 20 millisecond being a good target to debounce any switch. Okay, so I ended up going back and forth on these values quite a bit, but I ended up with 4.7 microfarads capacitor, 3.3K resistor here, and a 10K resistor to VCC. And so as you can see, this gives me more than 20 milliseconds on the button press and more than 20 milliseconds on the button release. And so this should be enough debouncing. So that's what I'm going to use. So let me wire this up permanently. I'm going to remove my probes. This here goes to the input of the inverter. And then I'm going to add a LED on the output so we can see what's going on. And the LED turns on. Perfect. Okay, so this should be our 3 clocks. I'm going to add the values that we determined on the KiCad schematic. Okay, so in terms of the values that we selected, the capacitor here is 4.7 microfarads. The resistor here is 3.3K, and this one is 10K. Then the resistor here is 220, and the pull-up resistor is 1K, and then the potentiometer is 500K, and we actually connected to pin 2 and 3, not 2 and 1. So yeah, so this is everything. Let me annotate. All right, perfect. Oh, actually, and this capacitor here is 1 microfarads, and this should be everything now. So I actually had to go back and remeasure all the resistors and the capacitors here for the pulse clock, because I had done all my measurements with a 74HCT14, and this one has different trigger voltages than the 74HC14 that I'm going to use. So these are the new resistor values. And I also added the unused gates, power supplies, and decoupling capacitors to our schematic, so it's now complete. Okay, so this feels like a good stopping point for this first video. We have built the 3 different clocks that we're going to use on the breadboard, and we have discussed what we're going to do with our output stage and, you know, how to do debouncing, that kind of thing. And so the next video is going to be about selecting between those clocks. We need to build a multiplexer circuit that will let us select between the clocks with button presses. And we're also going to work on the frequency divider so that we can divide the 28 megahertz all the way down into 1 megahertz. So I hope you enjoyed this one. Let me know in the comments if you have any questions or feedback. And I hope to see you in the next video. Goodbye.